Right, next up is solubility. So we're out of acids and bases now, but a lot of the same principles apply. What we're going to be discussing are things breaking down in water. We've written these types of equations last semester, we've written them this semester. All right? What solubility refers to is how much a species breaks down. It's the molarity quantity of ion in solution for this dissolution process. Okay? Insoluble compounds from last semester, they have a small solubility. So when we use that word insoluble, it doesn't mean completely insoluble, it means mostly insoluble. But now that we're at a situation where we understand equilibrium properties, we can really sort of get into the meat of that issue. What does it mean to be insoluble, and what is this small solubility? What are those little bits of ions that go into solution? How do we quantify that amount? So let's start with what we know. Last semester, we would look at something like KCl, and you would look at your solubility rules and you would say, oh, group 1A metal compounds, they're soluble. So if I put them in water, they break into a K plus, which is aqueous, and a Cl minus, that's aqueous, just purely. Okay? This semester, I told you, even if you have something where you would look at your solubility rules and it would be designated as insoluble, we still need to know that it breaks down. It breaks down into small amounts of Fe plus 3 and PO4 minus 3. Okay? Now that we're through equilibrium, soluble species are strong dissociations. They have an equilibrium constant that's so big that they just go completely to the right-hand side. So when we look at a reaction like the top one here, KCl, it's a soluble species, so it's definitely good to write it as a forward reaction. It's a strong reaction. Soluble species have strong dissociations. But insoluble species, all right, it's good to know that some of this occurs, but they actually have a calculable equilibrium constant. So in reality, what we should do is if something is insoluble, what it really means is it's weak. It weakly dissociates. It dissociates with a K that we can calculate. And it dissociates with a K that favors the reactant side. Okay? So solubility is now almost like how we understand weak and strong. Soluble, strong dissociation. Insoluble, weak dissociation. The equilibrium constant that dictates, right, how soluble something is called KSP. And it stands for solubility product. And that's because the ice tables associated with these sorts of equilibrium reactions, they have a sort of similar form. It always looks like a product of x's. And you'll see what I mean when we do an example here in a little bit, right? So this is an equilibrium, so it has a K associated with it. It's going to have a KSP. And guess what? That KSP is going to be small. It's going to favor the reactant side. So we know that some of this comes off, but not a lot, because the reactant side is favored. This also has a KSP, but it's like a strong acid with a Ka that's so big that we just might as well push everything to the right side. Same deal here. It has a KSP, but it's so big, we just say, oh, it's soluble. You can pretty much just assume that it breaks down completely. Okay? So these KSPs are things that we can calculate, right? And they'll give us how much ion goes into solution. And how much ion goes into the solution, we call that solubility. So the easiest thing to do is just kind of look at a couple examples with solubility to get your feet wet with doing the equilibrium problems again. We have to remember more from our initial equilibrium chapter. When we talk about solubility, the stoichiometry isn't as nice as our acid-base stoichiometry. Okay? We have to remember some other techniques here and there. We get so used to acid and bases where we just have everything is 1 to 1 to 1. That's not the case here. So let's look at something like SR3PO42. And we're going to do a couple of examples with this. So let's just start with this example right here with this. And I'll decide exactly what we're doing with it as we go through. We can look up this, and it has a KSP. And remember, that's the equilibrium constant associated with its dissolution. It has a KSP of 1 times 10 to the minus 31. Really tiny, right? Really small. This is something where last semester we would say it's insoluble because it doesn't fit any of the soluble species in our solubility rules. And we would say, oh, yep, in solution, we would expect to see a precipitate. We would expect to see a big chunk of solid sitting at the bottom of a beaker. If I put SR3PO4 in a beaker. And what this tells us, this small KSPs, it tells us, yep, that's pretty much right. But it's not 100% right. If we blow up a certain region here and we look, there is a tiny little bit of SR plus 2 floating around, and there's a little tiny bit of PO4 minus 3 floating around. And now that we have a K, and we know the equilibrium reaction associated with using that K, we can actually calculate these small little bits floating around. Okay, so let's do that. So here's how you're going to do problems like this. If I gave you an SR3PO4 to break down in water earlier in the semester, PO42, you would write this as 3 SR plus 2s, which are aqueous, plus a PO4, plus 2 PO4s, which are minus 3, which are also aqueous. You know how to do those dissolutions already. You kind of do them here the exact same way. The big difference here is we realize that this should actually be an equilibrium. And the equilibrium constant that describes the process is that. How do we deal with equilibrium? We make ice tables. We go ICE. We remember that solids, their activities are 1, so we cross them out. What we're going to do is we're going to calculate the solubility. So it's an insoluble species, sure, but that small amount of ion that gets released, we're going to be able to calculate a solubility. Whenever you're told to calculate the solubility of a salt, all that you have to calculate is an X. The way that all this notation, all this nomenclature, everything about solubility is set up so that KSP is the equilibrium constant, and whenever you calculate an X, the X is the solubility. Okay? So we have to remember, this isn't a simple one-to-one-to-one. We have to remember a little bit about how stoichiometry affects ice tables. You've been through it before, but we haven't done it in a little bit. Just get it back in your head. How much of this is in there to start with? 0. Q versus K. Q is equal to 0. We're going to move in this direction. We have to make 3 of these and 2 of these. So for equilibrium, right, there's going to be 3x, SR plus 2. But we really just care about X. X is the solubility. There's going to be 2x PO4 minus 3. It's the same X here. We just need that X. Well, we can take ice information and we can relate it to K. So we know that K is 1 times 10 to the minus 31. So 1 times 10 to the minus 31, our KSP, our solubility product, it looks like I should find my SR plus 2 concentration at equilibrium. But again, let's be careful. What do we do with it? We raise it to the 3rd power. All right. We should take our PO4 concentration at equilibrium. That's from the E spot of the ice table. And what do? We raise it to the 2nd power. So the big thing here is just remember that stoichiometry does affect these sorts of problems. So what is my SR plus 2 concentration? It's 3x. That whole entire amount has to be cubed. The 3 gets cubed as well. What's my PO4 concentration? It's 2x. The whole entire thing inside the parentheses, the 2x itself, the whole entire thing, including the 2, has to be squared. Again, not as simple and straightforward as acid-base ice tables, but not something that's beyond you guys. You've done this sort of thing in the past, okay? So let's just take this step by step. 1 times 10 to the minus 31 equals 27x cubed times 4x squared. So this looks like 108x to the 5th. Paying attention to rules of exponents. 1 times 10 to the minus 31. We can solve for x pretty easily here. The x that I get out is 2.4725 times 10 to the minus 7th. Okay. There would be one significant figure here because the KSPs are measured. So my final answer is you always just give your x. We're after the solubility is your x. So my solubility is 2 times 10 to the minus 7 molar. These KSPs, they have units of concentration for the species that go in. So any x that you solve for also has units of concentration. So it's just equilibrium in a different context. This is the solubility, 2 times 10 to the minus 7. Is this a big amount or a small amount? It's very small, right? So this tells you, all right, then you could use this x to figure out how much SR plus 2 you would expect to see in solution. Not a lot. How much PO4 minus 3 you'd expect to see in solution. Not a lot. But say you were doing some environmental analysis, biological analysis, where these small amounts could affect how you deal with that situation. Now we know how to calculate them. Okay. One more simple example of solubility. All it is just this equilibrium problem where there's this extra layering of what the word solubility means, how you use a solubility product. Let's go in the opposite direction for this example. The solubility of CuBr is 2.0 times 10 to the minus 4 molar. Determine its KSP. Again, this is small. It looks like it's not completely soluble. So it's going to have a calculable KSP. So what do? Oh, KSP, those come from dissolutions. Equilibrium problems associated with dissolutions of salts. CuBr, we know that breaks into a copper plus 1, which will be aqueous, and a Br minus, that will also be aqueous. We make an ice table. We cross out our solid. We know we start with 0 amounts of these because they're not given in the problem, right? If you don't see any information about it's going into something, you assume it's going into water. So there's 0 of this and 0 of that. Q is 0. That means we put our plus x's here. We get an x and an x here. Hold on a second. Let's see how this is working backwards. I mentioned that earlier. You're given the solubility. You're not given KSP. You're not given the solubility product. You're given the solubility. In this ice table, what's solubility? Solubility is x. So in this problem, you know x. Remember, the solubility always refers to that x. Now, this number is a lot bigger than the last number we saw. So this guy is more soluble than that SR3PO42, all right? But it's still insoluble from the standpoint of our solubility rules. It's still not a big number. Let's calculate its KSP. From our ice table, KSP is going to be equal to copper plus raised to the first power, okay? Br minus raised to the first power. Okay, well, that is nice for stoichiometry. It doesn't always have to be this way. These are at equilibrium. On my ice table, this was X and this was X, so my KSP is X squared. And what's given in the problem? 2.0 times 10 to the minus 4 is my solubility. That is my X. So this looks like our KSP is equal to 4.0 times 10 to the minus 8. Done, right? Just using our equilibrium tactics, our equilibrium ideas in another setting. One last quick thing. Remember the last example we had? The KSP was 1 times 10 to the minus 31. The reactant side is very favored. This side has a reactant side favored too, right? But which one is more soluble? More soluble, right? Because the K is a bit bigger than this K. And that's what we see up here in terms of the solubility. Associated with this KSP, and stoichiometry does complicate things, but associated with this KSP was 2.0 times 10 to the minus 4 molar ion concentration. It puts that many ions in solution, right? With this KSP, looking at that last example we did, we got 2 times 10 to the minus 7 molar ion concentrations. So the magnitude of K tells you how likely you are to dissolve. CuBr dissolves a lot more than our other compound from the previous example, but it's still insoluble relative to things like KCl. So all that work we used to do looking at K and deciding which side is favored, it matters here when you're comparing solubility of compounds, right? Where things start to get complicated is when we're not going into pure water. So everything that we've talked about so far and every KSP that you're given, it's all about going into pure water. So what do we do to modify the situation if there's already things there and it's not pure water? And we'll do that next time.